Hello and welcome back to the AICE Chemistry Lecture Series. In this video, we're going to look at Chapter 4, Section 9, which looks at bonding and physical properties and their correlations. So in this particular video, we're going to grab everything that we've seen in Chapter 4 and take a look at how all of these different topics, bonding, covalent bonding, ionic bonding, metallic bonding, and intermolecular forces correlate to the physical properties of the different compounds. Now, one of the things that's going to be important here whenever we discuss this is to always, when you're asked about physical properties, the very first thing you should think of is what type of compound am I discussing? Because when we look at the physical properties of how they are related to the bonding, you need to be very specific about, okay, am I looking at an ionic compound? Am I looking at a metal? Or am I looking at a covalent compound? Because those three subdivisions will have very different relationships with their physical properties. For example, let's take the first physical property into consideration. The first physical property we're going to look at is physical states at room temperature, meaning state of matter, solid, liquid, or gas. Based on the type of compound that we're looking at, we will have a different point of view on the physical state. For example, ionic compounds such as MgCl2 or ammonium chloride, NH4Cl, or sodium nitrate, NaNO3, any of these ionic compounds is going to be a solid at room temperature. Ionic compounds are always solid at room temperature, and there's a very simple and straightforward the reason for this. The melting points of ionic compounds are extremely high because of the strong electrostatic forces that hold the lattice together, aka the ionic bonds. This is all fancy terminology for saying ionic bonds are strong. Because ionic bonds are strong, they hold the lattice together really well, which means that all of these compounds are be solids at room temperature because they require a lot of energy for those electrostatic forces, i.e., or for example, ionic bonds, are going to require a lot of energy to break. So that's ionic compounds. They're always solid because they have really strong bonds. Metals are also solid at room temperature. So if we're talking about things like magnesium by itself, not magnesium chloride, or sodium by itself, not S, Na, or sodium by itself, or aluminum, or silver, or platinum, any of these metals are going to be solids at room temperature. There's only one exception that you need to memorize, which is that mercury is a liquid at room temperature. And you don't need to know why mercury is a liquid at room temperature. You just need to know that mercury is a liquid. But transition metals usually have really high melting points due to their strong forces holding the lattice together. Sounds familiar, right? It's the same thing that it says for ionic compounds. So what are these electrostatic forces? In this case, it is metallic bonding. So the metallic bonding in metals is really strong, which holds the lattice together, and therefore requires a lot of energy to break, keeping them solid at room temperature, and needing a lot of energy to melt them. Some metals have lower melting points, like group 1 and group 2 elements, for example, have very low melting points, but they're low in comparison to other metals. They're still solid at room temperature. Mercury is the weakest one, and that's why it's a liquid, but again, we're not going to discuss why that's the case. Finally, we have covalent compounds. Covalent compounds are the ones that are weird. Now, these are covalent compounds with simple molecular structures. They're the covalent compounds we have been talking about that you know, things that are molecules, so things like CO2, CH4, PCl5, any of those, any of those molecular compounds that are covalent that we think about now. There are other covalent compounds which we'll discuss in chapter 5, which have what we call a giant network structure, but we're not going to discuss them here. Now, these can have any state of matter at room temperature. We have different elements or different compounds that have different states of matter. Carbon dioxide, for example, is a gas at room temperature. So is methane. Water is a liquid at room temperature, and so is PCl5. Other ones are solids, like something bigger, like glucose. C6H12O6 is a solid at room temperature. So covalent compounds, covalent molecular compounds, come in a lot of different states of matter. And this is because they have usually low melting points due to weak intermolecular forces holding them together. And this is where it is very important that you understand what you're looking at. Covalent compounds, their physical properties are not dictated by their bonding like metallic and ionic compounds. They are dictated by their intermolecular forces. That's why we were talking about boiling point, we were talking about melting point earlier on viscosity. With covalent compounds, we were talking about intermolecular forces. So be very clear, when we talk about covalent compounds and their physical properties, we talk about intermolecular forces. When we talk about metals and their physical properties, we talk about metallic bonding. And when we talk about ionic compounds and their physical properties, we talk about ionic bonding. So bonding for ionic, bonding for metallic, but intermolecular forces for covalent. Because what's keeping the molecules near each other is not the bonds. That's what keeps the elements together. What's keeping the molecules near each other is their intermolecular forces for covalent molecular compounds. So that's for their physical states of matter. Now let's talk about their solubility in water. Now, with solubility, we generally have a rule that we're going to use for covalent compounds, and I will talk about that in a second. But let's talk about ionic and metallic compounds, because these are pretty straightforward. Ionic compounds are mostly soluble in water. Now, water is attracted to the charged ions in ionic compounds because water is polar, and they're going to form what we call ion dipole forces. Now, ion dipole forces are material for A-level chemistry, but essentially it's just the connection between a water molecule and an ion. So, for example, if we have water here, water has a partially positive and a partial negative side, partial negative oxygen, partial positive hydrogens. If we have an ion near water, for example, a sodium positive ion, that positive sodium ion and that negative oxygen on the water are going to attract. That's what we call an ion dipole force. We will learn more about these ion dipole forces and be a lot more specific about them in A-level chemistry. The hydrogen side of water, the positive side of water, can also form these forces, but not to a positive ion like sodium, but to a negative ion like chloride. If we have a negative ion, we can form an ion dipole force, so there's a force of attraction between the negative ion and the positive hydrogens in the water. So because of this, because water molecules attract chloride ions or negative ions to their hydrogen, and they attract positive ions to their oxygen, forming these ion dipole forces, they are mostly soluble. Now, why mostly? There are certain compounds that are not soluble, and you should remember them from the solubility rules that we learn in honors chemistry. Metals, on the other hand, metals are all insoluble in water. And that should be pretty straightforward, right? You throw a piece of iron in water, it's not going to dissolve. Otherwise, we would have bridges that go over lakes or rivers. The force of attraction between the metal ions and the delocalised electrons, aka the metallic bonds, are too strong. They're too great to be broken by water. Some metals may react with water, like some of the alkali metals do, but they will not dissolve in water. So that's pretty straightforward. Finally, we get to covalent compounds. Now, covalent compounds have a very simple rule. Again, because we're talking about solubility in water, Non-polar compounds are going to be insoluble, whereas polar compounds are soluble. Why? Because we have a rule in chemistry for covalent molecular compounds. Like dissolves like. What this rule is saying is that things that are polar will dissolve things that are polar, and things that are non-polar will dissolve things that are non-polar. Because water is polar in nature, then water will dissolve any molecular compound, every covalent compound that is polar. Whereas because water is polar, it will not mix and will not dissolve, therefore, things that are non-polar. So things that are non-polar are insoluble, they do not dissolve. Things that are polar are soluble, they do dissolve. And that's again because the water molecules that are polar are going to be attracted to other polar molecules that have a similar charge, dipole, positive and negative sides. Some covalent compounds, like acids, and this is something that you have learned and should keep in mind, are not just dissolved in water, but are broken down by water in a process called hydrolysis. Hydrolysis, this word, hydro means water, lysis means breaking up. So hydrolysis is the breakup of a compound or molecule by water. So acids are hydrolyzed. We learned already that acids will dissociate in water, and that's because they're broken up by water through the process of hydrolysis. So that's the solubility of different compounds in water. But again, if we're being asked, is something soluble in water, the very first thing we need to do is ask ourselves, what type of compound is it? Is it ionic, is it a metal, or is it covalent? And finally, the last type of physical property that we're going to look at is electrical conductivity. And we already discussed this to a certain extent. Now, something to keep in mind when we're talking about electrical conductivity is that electrical conductivity requires one specific thing: mobile charged particles. So what does this mean? Anything that conducts electricity will have a mobile, meaning it can move, charge, meaning it's either positive or negative, particle. So this could be a number of things. It could be ions that are moving around. It could be electrons that are moving around. But anything with electrical conductivity will have a mobile charged particle. If you're able to understand this, then you don't need to memorize what's conductive and what's not. You can actually reason it out. So for ionic compounds, for example, ionic compounds are only conductive when they're melted or dissolved in water. Why? In the solid state, there are charged particles in an ionic compound. You have ions. However, they're trapped in the lattice. They cannot conduct electricity because they're not mobile. However, when we melt or dissolve that ionic compound in water, those ions are freed from the lattice. They're released. They start moving around, they're melted, or they start floating around the water if they're dissolved, because ionic compounds dissociate in water. And so when melted or dissolved, the ions become mobile. Now we have mobile and charged, because they're either positive or negative, particles that can help with conducting electricity through the ionic compound, either in the melted state or in the aqueous state. Same thing with metals. We got to think of this again as mobile or charged particles. With metals, metals are conductive in every state of matter. We already discussed this earlier in the metals section. They're always conductive because metals in their structure have a built-in delocalized electrons in the metallic lattice. Those delocalized electrons are mobile charged particles. They can move around because they're delocalized. They're charged because electrons are negatively charged. And they're particles because they're subatomic particles. And so because metals in any state of matter have mobile charged particles, they have delocalized electrons, they're always going to conduct electricity. Finally, it brings us to the opposite of metals, which are covalent compounds. Now, other than a few exceptions which we will discuss in chapter 5, which are not molecular structures, covalent compounds are non-conductive. They do not conduct electricity. In fact, most of them are what we call isolated. insulators. Insulators being that they prevent electricity from going through. That's because there are no mobile charged particles in covalent compounds. There are no delocalized electrons, there are no ions in covalent compounds, and there's definitely nothing that moves around. Their molecules are fixed, all of the electrons are fixed within the molecules and their bonds, and so there is no mobile charged particle to conduct electricity, and therefore all covalent compounds are non-conductive. They do not conduct electricity. All right? So just remember, if we're talking about electrical conductivity, first of all, figure out if it's ionic, metallic, or covalent, like we always do with physical properties, and then think to yourself, does it have a mobile charge particle? If it does, it conducts electricity. If it does not conduct electricity. That is it for section 9, and therefore all of chapter 4. I will see you in the next video, and we'll start discussing chapter 5. Thank you.